All of us here at HGI would like to thank Solmax for creating and moving this webinar series forward, and also thank TRI, especially Abigail Gleason, for their participation and work on this series. And now, Deeply Filled Pond Surveys, the Solmax ELL webinar series number 4. With more and more geosynthetics being used for industrial and commercial and private containment projects comes the need for ensuring that non-permeable geosynthetic structures remain in good working order. Fundamentally, that means they are not leaking. I'm sure many of the people participating today have seen, touched, or felt a sample of geosynthetic liner. We may think that these materials are a robust barrier. However, when subject to extreme industrial conditions, we realize that they can be easily damaged. This means the potential for leaks to occur over the lifespan of these containment systems can be very high. So what do you do when that fateful day comes and you realize you may have a leak in your liner? We know that folks attending our presentation today are interested in learning about leak location technologies. You might suspect your pond has a leak, or a client's pond may have a leak, or you may be preparing for a future situation where this technology may be helpful. This presentation is designed to make you aware of the different technologies currently available, the fundamentals of how leak location in ponds work, and the best pathway through the process so it gets done right the first time. Throughout this presentation, we are going to discuss the big picture of liner leak location for ponds. This includes the physics behind leak detection, the different types of ponds, the design elements of those structures and how they impact leak detection sensitivity, survey layout, and different types of leak detection equipment. We will compare and contrast ASTM D7007 and D8265. And finally, we will leave you with some essential closing thoughts on what it takes to have these surveys done right the first time. Here is a situation we run into all of the time. You have a 25-acre pond that starts leaking and the leak rate violates local, state, or federal regulations. Your pond is placed out of service. This action impacts operations, maybe even causes some type of operational shutdown until the leak is fixed. You and your colleagues spend a significant amount of time and resources doing a leak detection survey. You have to drain the 175 million gallons to fix the holes and then fill it back up. What if after all that it's still leaking? What do you do? You now have to repeat the process until your system is compliant. You have to do it again. Take a moment and think of the tremendous costs that will be incurred not only if you have a leak, but also if all of the leaks are not found and you have to go through the process a second time. They are potentially huge. So what is the big picture? Well, as the previous slide mentioned, many of these structures are being scrutinized by governmental regulators whose job it is to make sure your ponds follow all the rules regarding their ability to contain your material safely and in an environmentally compliant way. Regulatory agencies establish allowable leak rates, also known as ALR, and operators are required to report any leakage above the allowable limits. ALR rates are different for each state. Case in point, California may be more stringent than Texas. Another example is that ALR for a double-line pond in Nevada are 150 gallons per day, whether they are 1 acre or 25 acres. Therefore, in a situation like this, larger ponds can be more challenging, not only to monitor, but to repair and maintain. If you have a leak, you will need to find a leak location provider to walk you through the process and get your pond back into compliance. Throughout the process, you will be responsible for several action items as the process moves forward. For example, making sure the pond is full as possible. If you have a double line system, the space between the top and bottom liners will need to be filled with fluid. Any grounded infrastructure associated with the pond will need to be isolated and powered down, and so on. Also, it would be really beneficial if the leak detection firm can subcontract the repair work so that the process is a total turnkey solution for you and your company. In the 1970s, solar evaporation ponds were likely some of the first large-scale uses of geosynthetic liners, and this is likely also when enterprising engineers started figuring out how to find leaks in these large geomembrane structures. The founder of our company, Dr. Jim Fink, tells stories of using electrical surveying methods to find leaks in geosynthetic lined ponds as far back as the 1970s. Starting sometime in the mid-1980s, geomembrane leak location surveys became commercially available and industry standards were developed in the form of ASTMs. The physics behind electrical leak detection in fluid-filled ponds lined with geosynthetics has been known about and well understood for more than 50 years and probably longer. Leak detection for geosynthetic liners is a proven, fully mature, science-backed technology, and when done correctly, it is exceptionally successful at finding holes in liners. The probability of success is based on the quality of the leak detection survey design and how leak detection techniques and methods are applied. The basic premise of an electric leak location survey is that electrical current will follow along the same pathway as water, i.e., currents will follow conductive paths and be impeded by resistive paths. The contained solution in industrial ponds is typically conductive. The geosynthetic liners are resistive, so when we apply current to a pond, current distribution spreads out uniformly through the liquid and current density decreases over distance. Any hole in the liner breaches the liner's resistive boundary, allowing current to flow through it. This creates a region of increased current density, which can be measured and located with high precision. Where the water flows, current goes. To find these areas of increased current density, sensors are deployed across the pond to map areas where the electric current density is greater than the area around it. Think of current density as flow, and the voltage would be the change in energy related to that flow. When we find a voltage anomaly, it indicates the location of leaks. Then we map where these voltage anomalies are so they can be repaired. Note, data acquisition methods and equipment for deeply filled ponds can differ for each ELL provider and are likely proprietary. For this presentation, data acquisition methods and equipment are represented by a black box. So here is the classic example. We have a pond with a conductive solution, a resistive liner, and conductive earth. We have current being applied to the pond represented by red electron bubbles. It follows a path of least resistance via a hole in the liner, creating a local area of elevated current. Accordingly, the electrical current relative to a hole in the liner is localized and measurable, while current levels remain low and uniform across the intact and undamaged liner. Mapping these differences in electrical current is how we locate leaks in any size pond. In this example, we have a double-line system. The leak detection method is the same as a single-line system, except for the addition of a secondary liner. In this situation, we are applying current to the fluid between the top and bottom liners. Again, the current being applied to the pond is represented by the red electron bubbles, and it flows through the solution and the resistive liner via a hole, while current levels are low and uniform across intact liner material. Water is a resistor, strange but true. Electrolytes carry current in a liquid, and they are substances that conduct electricity when dissolved in water. For example, common minerals such as sodium, calcium, and potassium are electrolytes when dissolved in a fluid. The term for this is electrolytic conduction. The ability of electrolytes to carry current depends greatly on the fraction of positive and negative ions available in a solution. So strong electrolytes form many ions, and weak electrolytes form few ions. This concept is essential to understand for electric leak location because if a solution contains too few ions, it will not be able to carry current for detecting leaks. Most industrial solutions contain plenty of electrolytes, but there are cases where the fluid is resistive. The opposite can be true as well. The information in the red box in the upper right is from the ASTM D8265, the Leak Location Selection Guide, and it states, if the solution covering the geomembrane is highly conductive, more advanced methods than those in D7007 may be required. For example, our technology works in ponds with resistive to highly conductive fluids. So if you have a pond with conductive fluids, it's important to seek out companies like HGI and TRI that have advanced methods to locate leaks in these types of situations. The definition for a deeply filled pond is extremely broad and really depends upon who is talking. It could be a few feet deep or more than 50 feet deep. The distinguishing factor is whether or not a person can wade through the pond to perform a leak location survey. This does not mean that deep pond methods cannot be performed on shallow ponds that are 3 feet or less, but shallow pond methods cannot be performed on deep ponds greater than 3 feet. So let's look at some examples of deeply filled ponds. Within each industry, there are ponds specific to their industrial processes. In mining, for example, we have tailing storage facility ponds, PLS ponds. PLS stands for pregnant leaching solution, desilting basins, emergency event ponds, evaporation ponds, and settling ponds, just to name a few. What's also interesting is that within each industry's subset of ponds, there will be a variety of fluid types, such as extremely high or low pH levels and significant variations in TDS and electrical conductivity. These types of fluids can be very common in chemical ponds, as well as mining ponds and others. And remember, the types of solutions can determine if the leak location provider can find holes or not. Decorative or recreational ponds are another type of ponds, and they usually are associated with housing communities, reservoirs, or stormwater ponds. We also have agricultural ponds, such as winery ponds, irrigation ponds, livestock ponds, and many others. These ponds can be high in TDS and pH. Every pond is different and will benefit from a unique survey design, which considers, for example, electrical isolation, how the pond was constructed, how it operates, its size, its infrastructure, its location, fluid chemistry, and a whole host of other unique aspects that ponds may have. And all of these considerations need to be addressed up front before we have even mobilized to the site. This enables us to optimize leak detection against the survey cost and scheduling. Electric leak location is governed by this influence between the solution's electrical properties, the resistive nature of geosynthetic liners, and the degree of electrical isolation obtained in the area to be surveyed. We can think of it as the electrical properties of the contained solution are the current carrier. The resistive nature of geosynthetic liners is the current resistor. And electrical isolation is the ability to confine current to the survey area. We know electricity follows a path of least resistance, much like water flows through a pipe or in a river. This is the classic analogy useful for explaining Ohm's law and how these three variables interrelate with each other. In a geosynthetic containment system, the solution filling the reservoir is used to carry current through the survey area. Electrical isolation will ensure that current is available for the leak location process. However, any electrical pathways grounded to the outside world in the survey area can bleed off electrical current needed for leak location. Thus, it is crucial to create a temporary electrical isolation state for the survey area to increase and maintain leak detection sensitivity. The level of electrical isolation can influence the ability between finding every hole or nothing at all. In the top example, there are two problematic areas. These are conductive pathways allowing current to escape from the survey area. What's happening is that there are strong current paths created between the current injector and the outside world in this scenario. The first issue is the pipe, and the second is the land bridge connecting the fluid in the pond to the native material outside the pond. Both these issues will prevent a successful leak detection survey because electrical current is now flowing through your infrastructure, which is the path of least resistance. In the bottom example, we show a survey area demonstrating good quality electrical isolation. The good quality electrical isolation of which the pipe and the soil bridge are no longer present, and the path of least resistance for electrical current is via any hole in the liner. The previous example shows the important relationship between electrical isolation and sensitivity. When considering the great difference in design from pond to pond, it's easy to see that good isolation leads to good leak detection sensitivity, which will lead to a successful leak location survey. Some different types of infrastructure that need to be isolated are any pipes below the waterline, any electrical equipment such as water pumps, concrete features that protrude through the liner, and soil or riprap on top of the liner. All of these will need to be closed off, confined, or sealed. Whether a pond is single or double lined will also present different challenges. For the single line system, the substrate below the liner must be sufficiently electrically conductive to carry current. This is rarely an issue, but can happen and will prevent a successful survey. For double line systems, there is often more infrastructure. There will be electric pumps related to the sump and moving water in and out of the structure. They will all need to be powered down and disconnected, and in some cases, removed. The interstitial space between the primary and second liner will also need to be flooded so current can flow between the liners should there be a leak. Note that the bottom or secondary liner cannot be tested in double line systems unless a network of permanent monitoring electrodes was installed when the pond was constructed. Other factors in leak detection sensitivity are measurement density and line spacing. As we can see in the image below, most surveys follow this turnstile approach where a sensor takes measurements as it is pulled across the bottom of a pond. When it gets to the other side, it is moved laterally some distance and then pulled back across the pond to collect another line of data. This continues until the whole pond is surveyed. The distance between the data points and the line spacing is a function of site-specific conditions and will vary from pond to pond. For example, the level of fluid conductivity or resistivity and isolation factors can all affect data point spacing and line spacing. If data points and line spacing are too far apart, then leaks could be missed. A few slides back, we discussed electrolytic conduction, the fact that electrolytes conduct electricity when dissolved in water, and how ASTM D8265 suggests more advanced leak location methods are required for highly conductive fluids. The challenge here is that conductive solutions reduce the resolution of many current leak location technologies on the market today. There are advanced leak location methodologies such as ours that have overcome these challenges due to conductive solutions. So if you have a pond with highly conductive liquid, be sure to seek out a service provider that can work in that type of environment. So now let's talk about signal masking, also known as signal shadowing. That is, the size of a leak can impact sensitivity and reduce the ability to find smaller leaks near a larger leak. Here is a case that if all other sensitivity factors are accounted for, some leaks can still be missed because they are obscured or masked by more significant leaks, creating a much larger leak signal. Remember, all leaks in a system create current paths between the current injector and the leaks. So a larger leak can potentially create a stronger signal, and that signal can sometimes mask smaller leaks nearby. Throughout this presentation, we have discussed several critical factors focused on what it takes to perform a successful leak location survey. By this point, it should be very apparent that the #1 factor in designing and executing a successful survey is the degree of electrical isolation that can be generated and maintained in the pond survey area. Pond design elements can have major impacts on the ability to find leaks if they reduce or increase the pond's electrical isolation. For example, perimeter isolation can be a big challenge. Here we have a decorative pond covered with a layer of soil. To isolate the pond electrically, an isolation trench had to be installed to keep current from bleeding off the survey area into the surrounding environment. The trench had to be dug down to the liner, exposing a small ribbon of geomembrane around the entire perimeter of the pond. Only after this occurred could an electric leak location survey be performed. Here is an example of where an isolation flap was welded on during construction to help maintain perimeter isolation of the survey area. An isolation flap is just a thin piece of plastic that protrudes through the soil to isolate the inside from the outside of the survey area. If this same method was used on the pond in the last slide, much less work may have been needed to perform the survey. Here is another example of isolation issues associated with design. On the left, fluid simply flows on top of the pond liner to fill the pond. Current can bleed out of the system through the waterfall, so the fluid will need to be diverted away from the survey area to increase the isolation. In the image on the right, we have a pond with two cells. In this scenario, water can be diverted from one cell to another, allowing the facility to continue operation while leak location and repair is completed in the leaking cell on the other side. Here is another challenge: complex infrastructure. In this situation, concrete and metal structures were erected through the liner to hold a pipe above the pond. Complex welds are needed for structures like this, and many leaks can be associated with such features. Limiting infrastructure complexity can help make leak location much easier. In this example, bird balls can make access challenging for surveying. However, a simple fix is adding additional fluid to the pond to help disperse the bird balls, making access to the water easier. Bird netting is another option, but it too has its own set of issues related to access. There are also bird cannons which can help by scaring away the birds. Pipe penetrations below the waterline are a challenge as well. A good alternative is to consider using pipes on the surface along the rim of the pond. Here there is much greater access to isolate the pipes if needed. If your pond already has these types of penetrations, they will need to be plugged, and if they are metal, they will need to be both sealed and plugged. Here again, we have a situation where there are many complex welds, and the pond will need to be drained to plug and seal the pipe for isolation. Plastic pipes should always be used if possible. If for some reason the pipes below the waterline cannot be isolated, then holes in the liner cannot be detected within a certain radius of the pipe penetration. In this situation, a stainless steel pipe is placed over the liner's edge, bridging the fluid inside the survey area to the ground outside. The solution to solve this problem was to create an air gap between a pipe joint to isolate the pipe. As we mentioned before, much of the leak location equipment used by the different leak location providers is proprietary technology, and as such, we can only give limited information concerning how this equipment works. There are two types of sensors, ones that sink to the pond bottom and are towed back and forth across the pond in a grid-like pattern using ropes and cables. And there are also ones that float on the surface, and they are towed back and forth in a grid-like pattern as well, again using ropes and cables. For towed probes, they are pulled a discrete distance and a data point is taken, and then pulled the same distance again and another data point taken. This is repeated until the entire pond is covered. Or they are simply pulled continually across the pond while data is acquired as they move. Floating arrays are similar to the towed bottom probes. The only difference is that they are pulled across the surface of the water. They are pulled a discrete distance, a data point is taken, and then pulled that same distance again and another point taken. This is repeated until the entire pond is covered. They, as well as the towed bottom probes, can be pulled across the pond continuously while data is being collected as well. This is another type of sensor and data acquisition style that we use here at HGI. This is a 50-second video cut from a larger promotional video demonstrating HGI's methodology.
With 30 years experience and an on-site geophysicist, HGI sets the industry standard for success rates, finding leaks quickly and accurately on the first try. Here's how we do it. Custom-built cables with leak detection sensors are deployed throughout a pond. Transmitters placed strategically around the pond deliver electrical current under the liner. Liners block current, so where the water flows, the electricity goes, pinpointing even the smallest leaks. Leak found. HGI's method works in any type of pond, single or double-lined, and in any type of solution. Wastewater, PLS, stormwater, chemicals, or brine. HGI's method even works in conductive solutions, which is next to impossible using traditional approaches. HGI's unique method is also safer. Our crews never enter the pond.
The fundamental difference between D7007 and D8265 is how each method manages data acquisition. Both ASTMs describe the basic steps in performing a leak detection survey in a fluid-filled pond. D7007 is the original standard, and D8265 adds additional technology advances. So how does D7007 work? Well, D7007 towed probes are typically a dipole configuration. They stay on the surface of the liner under the solution and acquire data. The probes convert the imposed electrical signal in the pond to an audible tone. The operator must listen attentively as the tone changes in amplitude based on the electrical current associated with a hole in a liner. As the dipole gets closer to a leak, the amplitude of the tone increases, and as it moves away, it decreases. Peak amplitude of the tone indicates the probe is at its closest point to the leak. Leak positions are located based on the distance along the cable and the line number. For this method, data is collected but not stored, and so there is no data processing. This limits the ability to review the data from line to line and tease out different leak responses. This method depends on the human response to how loud the tone is, their understanding of where the probe is under the water, and their ability to remember the tonal differences from line to line. There is also probe drift. Liners are not nice and flat, and so the probes can go offline pretty easily and follow a wrinkle. Lastly, this method may not be well suited for highly conductive solutions. Now let's take a look at the ASTM D8265. For the D8265 method, data is required to be collected and presented in a report. This holds leak detection firms to a higher standard of scientific reporting. For this method, a probe is deployed into the pond and pulled across the liner a discrete distance. A data point is taken, and then the probe is pulled the same distance again, and another data point taken. This process is repeated throughout the pond. The data are reviewed during data collection, then again at the end of the day's work, then again after the survey is completed to ensure that all leak responses are identified. Following data collection, the complete data set is processed, and then a voltage map is created to determine the location of leaks. For example, in a few years from now, we can go back and review the data should it be necessary, as repairs can be delayed. Using this method, much of the subjectivity is taken out of the process as data is acquired, recorded, analyzed, and plotted. Here are examples of the D8265 ASTM method. The ability to map data and review the finer details increases the ability of finding leaks that might have been missed without a data review. For example, not all leaks have a large leak response, and data review can tease out smaller leak responses, creating a more successful survey. The following plots show the power of data presentation. In this example from TRI, we see the data from a leak survey presented visually. We can clearly see the location of the current injector surrounded by leak responses. Data processing, data analysis, and data presentation are a significant advantage to the leak location process, confirming leaks and reducing false positives, offering the highest quality results. Here are some data plots using our method and technologies. On the left, we see a classic contour plot highlighting the location of various leaks. On the right, we use software and data analysis to show the magnitude response of each leak anomaly, giving an idea of relative leak size from one anomaly to the next. In this particular project, the client decided to fix the largest responses only, which were located on the perimeter of the pond higher up in elevation on the slopes. They were able to become compliant with state regulations after repairs were made and the pond was put back into operation. In this slide, we show a comparison of ASTM D8265 on the left and D7007 on the right deliverables. While both show leak responses, the D8265 plot shows supporting data. The option exists to review the D8265 data multiple times so that all leak responses are identified. This can be useful during the repair stage when the liner repair company is reporting back their findings to the leak detection company so that interpretations of the data can be confirmed. Some closing remarks. Getting it right the first time is important. Having to perform a second leak test poses serious risks for operation, production, and costs. When a leak detection survey is conducted according to ASTM D8265 standards, the chance of doing it right on the first attempt is significantly improved. The following lists are some of the savings in either time or money when a leak detection survey is performed the first time correctly. Savings in pumping costs. After a leak location survey is performed, the solution in the area will need to be removed so that you can do liner repairs. There are savings in regulatory fines. Savings in liner repair fees. If you have to do a second leak location test, you will also have to do the liner repairs a second time. There are savings from only performing the leak detection once. And there are savings in labor costs as well as in stress. And there are savings in the prevention of facility shutdowns. Some final thoughts. Work with a leak detection firm that will meet the needs of your specific pond. Remember, ASTM D8265 has a greater success rate of locating leaks and fewer false positives. This will save you money and time, making sure your survey is done correctly the first time. Make sure to check for references provided by your leak detection company during the bidding phase. If your references are happy, it is very likely you will be happy. Ensure your pond is electrically isolated when possible before performing the survey. And if you are uncertain, make sure you communicate with your leak location provider. And remember, new pond construction should consider design elements that ensure proper electrical isolation so that future leak detection surveys are possible and successful. Thank you for attending our presentation.